Experiment of Coulomb's law. Purpose: to verify the inverse square relationship and the charge dependence in Coulomb's law using the Coulomb balance. Coulomb law apparatus. This is the device of the Coulomb law apparatus we use in this experiment. Theory: Coulomb's law states that the magnitude of the electrostatic force of attraction or repulsion between two-point charge is directly proportional to the product of the magnitudes of charge and inversely proportional to the square of the distance between them. Coulomb's law states the force of attraction between unlike charges Q1 red and Q2. There is the force of repulsion between like charge, like this diagram, that F equal K Q1 Q2 over R squared. Q1 and Q2 are electrical charges, R distance between charges. So, what is the K?
Formula, there are two important pieces of information. One of them is that the force varies inversely with the distance, such that increasing the distance will reduce the force, and the force varies proportionally with each of the two charges, such that when we increase the value of the charge, the force becomes larger. And this is what we are going to examine in this experiment. We are going to examine these two facts in two different parts. So this experiment consists of two parts. In part one, we will examine the relation between the force and the distance, which means we are going to measure the force between two charges for several distances, and we can then make a drawing that tells us what is the relation between them. In this experiment, as you will see in the video, we will have the following: a fixed charge. The two charges are going to be two spheres, and we will put charges on these two spheres. One of these two spheres is fixed, not moving, while the other sphere is connected to a rotating axis. Now we will put same sign charge on both spheres. They will repel each other with a force. Now this charge is fixed. It is not going to move, while this charge, which is not fixed, will rotate like this. Now this rotation angle, in fact, this rotation angle, by how much does this ball rotate, this depends on this force, such that when this force is stronger, the ball is going to rotate more and the angle becomes larger. When this force is smaller, the ball is going to rotate with a smaller angle. So finally, after finishing this part, we will have a table with several values of the distance and several values of the angle taken. And of course, we will choose a certain distance, here are, between the two balls. And at this distance we measure an angle, so we will get the first reading. Then we increase or decrease this value, this distance between the two balls, and at the new value of the distance we measure another value for the angle of rotation. Then we change for a third value of the distance, and for this third value of the distance we measure the new value of the angle, and so on. So finally we will have 5 readings for the distance and the angle. And since we are going in this experiment study only the proportionality, so we are not interested in the exact numbers. So we will replace the force by the angle. So we will study the relation between the angle and the distance. We are supposed to make 2 graphs. The first graph is theta with r, and this graph is supposed to look like this, which proves that this relation is inverse square law, since this shape looks like f equals 1 or f of x equals 1 over x squared in mathematics. The shape is exactly like 1 over x squared. So we are sure now that the force varies with r as 1 over r squared, as Coulomb's formula says. And to make sure that the power is 2, we can convert this graph into a straight line by graphing the angle theta with 1 over r squared. So we put 1 over r squared because this is from this formula. We can write k q1 q2 1 over r squared. We can write this Coulomb's formula in this form, which converts this to y equals mx. So if I put 1 over r squared on the x-axis and f or theta on the y-axis, then this must be a straight line with this slope. This should be this slope. So if doing this converted the graph into a straight line, then we become sure that the power is 2. So we will add here a third column with the values 1 over r squared. And in the experiment we are going to fill only these 2 columns, and the third column is something you fill at home from your values. If for example r is 5, then this is 1 over 5 square. If r is 10, this is 1 over 10 square. If r is 15, this is 1 over 15 square, and so on. Now in the second part we will study the relation between the force and one of the 2 charges, which is the fixed charge. So we will keep the charge on the moving ball as it is, not changed, but we will have several values of the charge on the fixed ball. I will call it Q1. So we will keep the value of Q2 fixed and change the value of Q1, and we will do the following. We will study this relation now. F equals K Q2 over R squared times Q1. Now, in this part, this should be fixed. So we will use a fixed value of R. So we are not going to change the distance between the 2 charges. but we are going to measure the force for several values of Q1. And for the charge Q, instead of the charge, we will change the charging voltage, because when we change the charging voltage, or when we increase the charging voltage, this will give more coulombs to the sphere. And we are going to use voltages of 2 kilovolts and 3 kilovolts and 4 kilovolts and 5 kilovolts and 6 kilovolts, 5 readings. So whenever I increase the charging voltage, by doing this I will increase the value of the charge Q1 in this experiment, and for each value of voltage we will measure the angle theta again, which is the same idea. This is the sphere, this was the original location of the sphere, and this is the fixed sphere, and we measure what is the rotating angle caused by this force of repulsion. This is the fixed sphere. So what we are doing now, we charge this with 2 kilovolts, we measure the angle. 3 kilovolts, we measure the angle. 4 kilovolts, of course, increasing the voltage will increase the force, which will increase the angle. So we'll have 5 readings of charge. In fact, it's 5 readings of voltage instead of the charge. So the voltage stands for the charge and the angle stands for the force. And this is something we can do only in our case, since we are studying only the proportionality. So we are not interested in the exact values, exact number. We need just to see what is direct proportional with what and what is inverse proportional with what. So I expect this to be a straight line, since this is our relation. If I put theta on the y-axis and the voltage on the y-axis, how many kilovolts, I expect a shape like this. Force is placed on the y-axis, or theta, and Q1 is placed on the x-axis, or instead of the charge we put the voltage, and this becomes the slope of our line, KQ2 over R square. But we are not going to ask you to measure or to calculate the slope, since we are not using the values of the force and the charge. We are using something else, which is the angle and the voltage. Now this is the theoretical part of this experiment, and you can see the instrument used and the steps of doing the experiment in the coming video, inshallah.
This is the instrument we are going to use in this experiment, and as you can see, this instrument consists of 2 plastic balls, these 2 balls, and these 2 balls will represent the 2 charges. We are going to put charges on them, and they will affect each other by a repulsive force, since we are going to use the same sign charge. And the distance between the 2 balls can be measured here from this ruler. This sphere is able to move back to increase the distance between the 2 balls, and forward to decrease the distance between the 2 balls. And the distance is something we can read from this ruler. So at this location, for example, the distance between the 2 balls is 9 centimeters. The distance, by the way, is measured between the 2 centers. So the distance is now 9 centimeters between the center of the first ball and the center of the second ball. Before starting the experiment, this protractor that measures the angle should be at 0, and this moving sphere, now by repulsion, one of the two spheres, which is this one, will be repelled away and it will rotate like this. And when the force of repulsion is larger, the sphere will rotate more and more with a larger angle. And to measure the force, we will measure the angle of rotation such that the angle is proportional to the force. So we are not going to measure force in newtons, we are going to measure angles in degrees, since the angle represents the force. And at the beginning of the experiment, you can see here at this point there are two black lines. When there's no force, these two black lines must be fixed like this, opposite each other. Now, how to charge these two spheres? We have the power supply, this one. This one is connected from the positive terminal with this pointer. This is the pointer. This is the pointer connected with the positive terminal where we can charge the spheres. And for safety, the negative terminal here from the back should be connected to ground or any metal. So I will connect this with this, for example, key, just to be grounded. Now this power supply, when turned on like this, it can supply voltages up to 6 kilovolts. As you can see, the minimum voltage of course is 0, and we can increase the voltage up to 6 kilovolts. This is 1 kilovolt, 2 kilovolts, 3 kilovolts, 4, 5, and so on. So this head is now at this position is 6 kilovolts. So when I touch the ball, it will be charged with 6 kilovolts. Now, as I told you in the introduction, this experiment consists of two parts. In the first part, we will fix the voltage. So I will use a fixed voltage of 6 kilovolts as I showed you. Then I will charge the spheres by just touching like this. So when I touch the sphere, now this sphere is charged with 6 kilovolts. Then I touch the other sphere again to charge this sphere. Now this is a big problem because this sphere will keep moving. Okay, now we are ready for the first reading. I adjusted the distance between the two spheres to be 20 centimeters, as you can see here. And because they both carry a positive charge, charged at 6 kilovolts, this ball, the moving ball, this one, is rotated to the left, and we need to measure the angle of rotation. As you can see here, it is rotated from the 0 location. Now, how can I measure this angle of rotation? I can use this one and move it back like this. Okay, until the sphere goes back to its 0 location, and I can measure the angle easily like this. Now it came back to the 0 location and the angle is 5 degrees. Okay, now for the next reading, I will move this ball to a distance of 14 centimeters. And by doing this, I noticed that this sphere is rotated again, and it's again not at the zero location. There's angle of rotation, is rotated again to the left, and to move it back I must rotate this to measure the angle. More until it comes back to its zero location, like this, which means the angle was a little bit more than 10 degrees. So all what I have to do now is to repeat this procedure by changing the distance again and again and again. We will use a distance of 10 centimeters, measure the angle of rotation again, then 8 centimeters, measure the angle of rotation again, then 6, then 5, until I finish the readings for this part. And finally, after doing this experiment, I came to this final result for this part. So at 20 centimeters distance, the angle was 5, at 14 it is 10.2, at 10 it is 20, at 8 it is 31, at 6 centimeters the angle was 55 degrees, and at 5 centimeters the angle was 80 degrees. Notice that the distances are in centimeters, and that whenever you increase the distance, the force becomes larger, which makes the angle more and more. Okay, now we will go to the second part of this experiment. In this part, we will study the relation between the force and the charge, one of the two charges. So we will fix the charge of one of them, which is this moving ball. We will fix its charge at 6 kilovolts from the first part, but we will change the voltage of the second ball. So this second ball first, I will touch to this charge. Now it carries no charges at all, and I will charge this ball at 2 kilovolts. As you can see here, I will take the pointer, touch the sphere like this. Okay, now the sphere is charged with 2 kilovolts, which causes this other sphere to be repelled away. As you can see, the two black lines here. Now to move it back to its zero, I must use this one. Back like this. Okay, until this sphere comes back to its original location here, from which I can see that the rotating angle was 6 degrees. Now to take next reading, I must increase the voltage to 3 kilovolts. Touch the sphere again to increase its potential from 2 to 3. But we do not touch the other sphere because we want its charge to be fixed at 6 kilovolts. Now by increasing this, I noticed that there's a small repulsion, and this moving sphere is now moved a little bit from the zero.
Calculate the electric force between charged objects. So, this equation shows the magnitude of the electric force between charged particles. F is equal to the product of the two charges Q1 and Q2 divided by the square of the distance between them, R, and then multiplied by the proportionality constant K. The electric force is expressed using the unit Newton. The reason why the distance is squared is because when the distance between objects doubles, the force between them reduces to a quarter of their original value. In other words, the electric force between two objects increases as the distance between them decreases, and opposite, the force decreases as the distance increases. The lowercase k is called proportional. To sum up, Coulomb's law states: the force between two like point charges is repulsive, and between two unlike point charges is attractive. The force direction is determined by the line that passes through both charges. The magnitude of the force is directly proportional to the product of the two charges and inversely proportional to the square of the distance between the charges. Being a force, the strength of the electrical interaction is a vector quantity that has both magnitude and direction. This means that we can calculate the magnitude and the direction of the electric field based on the sign of the result. Let's modify the equation. The arrows in the equation represent a vector quantity. This sign means that this is a unit vector pointing from Q1 to Q2, and the index 1, 2 means that Q1 exerts force onto Q2. If we get a positive value, it means that the direction of the force is repulsive. On the other side, the minus sign means that the direction of the force is opposite or attractive. Let's say we have two positive charges. The first charge, Q1, is 2 times 10 to the minus 2 coulombs, and the other charge, Q2, is 1 times 10 to the minus 3 coulombs. The distance between them, r, is 1 millimeter, which is 1 times 10 to the minus 3 meters. Now we can calculate the force between these charges using the equation. So F is equal to K multiplied by the product of the two charges Q1 and Q2 and divided by r squared. Here we can cancel out meters and coulombs, which means that we are left with newtons. This is 18 times 10 to the 4th divided by 10 to the minus 6th, which is 18 times 10 to the 10th newtons. We got a positive result, meaning that the charges repel one another. In case we had one positive and one negative charge, we would get a negative result, which means that they would attract one another. If there are multiple point charges, let's say 3, we can calculate the force of the two charges that acts on the third charge. This leads us to the superposition principle, which states that for all linear forces, the total force is a vector sum of individual forces. This allows the Coulomb's law to be extended to include any number of point charges. In other words, the total Coulomb force from a system of point of charges acting on a point charge can be found by adding up the forces from each of the other individual charges. Here's an example. We have 3 point charges, Q1, Q2 and Q, and we need to find the force that Q1 and Q2 exert on Q. Q and Q1 are positive charges, and Q2 is negative charge. The force that Q1 applies on Q, F1, is repulsive, and the force that Q2 applies on Q, F2, is attractive. The total electric force F is a sum of the two forces, F1 and F2,